All right, welcome back, everyone. Welcome to day 15 of Organometallics class. Just a few administrative points. So first off, thanks everyone for submitting your drafts of your Wikipedia articles. As a reminder, and hopefully everyone should have received your peer review assignments. As a reminder, the peer review is due on Wednesday at midnight. And so I think you can think of this as how you might think of peer review for a journal article you might be asked to review. Try to offer fair and productive feedback and approach it with the mindset of trying to provide at least a couple points that help to make the article better, because ultimately these articles will be the product of the general scientific community. So it's important that that they're as good as they can possibly be. Okay, are there any questions about the Wikipedia project or any other administrative points before we jump in? Okay, if not, let's begin by just very quickly touching back on problem of the day number 2 last time, which I realized after class while I was walking Hermione that I totally screwed up the explanation for. So I sent out an email that provides the correct explanation. So just in case anybody didn't see that or didn't get a chance to go over it, let me revisit that. So the problem asked one to think about the regioselectivity outcome of a palladium catalyzed allylic substitution, where the intermediate, which is not drawn here, but is this unsymmetrically substituted aryl prime metal pi al. Of course, the nucleophile can add to either of the 2 carbon atoms, and these give different selectivity outcome. And so the correct way to think about this is there are a few different ways one can think about this and get to the right answer. And I had this in my notes, and then I thought of a shortcut for how to explain this, and then explained the completely wrong answer. So one way to think about this is that remember that even though pi alols, in terms of how we draw them in terms of formalisms in coordinating to the metal are al anions, in practice, in terms of their reactivity, they act much more like al cations. And so as a first approximation of thinking about their ground state electronic configuration, you can think of them as al cations. And in this case, if you think about a nitro-bearing aryl group or a methoxy-bearing aryl group, the 2 ground state stabilities one would expect to be quite different. And of course, it would be more favorable to put the cation distal from the electron withdrawing group and proximal to the group where the methoxy can donate electron density through resonance. And so indeed, this is how the nucleophile preferentially attacks, and that's manifested in the outcomes shown here. And as I alluded to in class, this can also be predicted by looking at the NMR resonances of these 2 carbon atoms. So this C13 shift is shifted downfield compared to this C13 shift. And so this tangentially has to do with how any alkene, the polarization of any alkene or conjugated polyenol system depends not just on the proximity to an electron withdrawing group, but whether that electron withdrawing group is in the appropriate conjugation or not. Okay, that's all I'm going to say about that. Are there any questions? It's a, you're saying it's a...
Yeah. For the carbon cation.
Okay, yeah, so as I mentioned, I guess for me, I think of this as a mnemonic that allows you to think about the correct outcomes. The question you're asking is a little bit different, which is what is the thermodynamically predicted product outcome? And off the top of my head, I don't know, but I do know that this, I mean, and you, I'm sure, can appreciate this too, this is the more thermodynamically stable product. And this is the less thermodynamically stable product. So it's consistent with thermodynamically expected outcomes as well. But I think that the reaction has a significant kinetic component to it. So yeah, that's another way that you can think about it. I talked about this in the email that the thermodynamically favored product is the major product in this case. And another way that you could think about this, if you want, is that during the nucleophilic attack, here you have a transition state with a dipole moment where electrons are flowing to the more electron withdrawn aryl group. So that is also favorable from a kinetic standpoint. Okay, so the bulk of today's class will focus on olefin metathesis, a really exciting topic and one that's near and dear to my heart. So we'll begin by talking about some general features and considerations of olefin metathesis reactions, and then we'll get more into the nitty-gritty detail. The history of the development of this reaction is really fascinating. I won't be able to do it justice. Of course, this happened over the span of about half a century. But I will try to highlight some of the key historical turning points, if you want to think of them that way. And I'll provide references so that anybody who wants to dig deeper has the means to do so. So we'll start just by reviewing something that we talked about earlier in class, which is thinking about how metallocyclobutanes, which can be accessed via 2+2 cycloaddition between a metal carbene and an alkene, can react via several distinct pathways to give different product outcomes. So in one case, after, and the case that's going to be most important for today's class, after 2+2 cycloaddition, the system can undergo retro 2+2 and I'll draw that here. And now I see that I've managed to draw the wrong. Doesn't really matter, but just for the metallocyclobutane I drew the wrong products. Okay, so it can undergo 2+2 and then retro 2+2, where you have this, as I'm sure people have learned in class, this swapping of partners around the ring. You can also, the system can also undergo reductive elimination. We saw this previously, to give a cyclopropane and now reduced metal species that does not contain the carbene. Lastly, the system can undergo beta hydride elimination. So from here, note that there's a beta hydrogen at this carbon atom, and so beta hydride elimination then would give a al metal hydride, which of course can undergo CH reductive elimination to give an alkene product. And note that these two are constitutional isomers of one another. In this case also, you have a reduced metal species where you've lost your carbene. And so which of these pathways is operative, as one might expect, depends on some of the predictable factors like the nature of the metal that's involved and the nature of the ligand set on this metal. As a general first approximation, as you move right in the periodic table, pathways of the bottom two type are going to become more common. And so this is why, for example, there are no known effective rhodium-based olefin metathesis catalysts, because rhodium is too far right on the periodic table. Those systems would prefer to undergo this way, these pathways. So an important factor, particularly for ring opening metathesis polymerization, is ring strain. This also manifests itself in other types of reactions like ring opening cross metathesis. But I didn't really have another. This we could cover later, but it fit nicely in this part of the blackboard, so I just thought I'd throw up these numbers here so that you can keep them in the back of your mind. It's important to remember that for small rings, 5-membered, 6-membered, these contain minimal strain energy, and then for medium-sized rings, 7, 8-membered rings, they start to contain substantial strain energy. And these then start to become good monomers where there's minimal backbiting as the propagating chain grows. And then bridged species bridged alkenes are particularly strained and are some of the most kinetically reactive monomers, kinetically and thermodynamically reactive monomers in play. And so I think that at the very least, this is an important thing to keep in one's mind about predicting how easy or difficult it might be, for example, to close a certain ring size if one wishes to use ring closing metathesis. So there are several different categorically distinct, well, you could argue how categorically distinct they are, but several different classes of related reactions, all of which have importance in various aspects of synthetic chemistry. And so I've highlighted those here. So one, and the oldest and arguably the most, well, arguably the most sort of broadly, widely used in terms of scale version of olefin metathesis is just the simple redistribution of alkene substituents in the context of the Shell-Haier olefin process. So this is the process by which ethylene is converted into useful feedstock compounds like linear alcohols. And so after controlled oligomerization of ethylene to higher alkenes, then the alkenes can further be redistributed using heterogeneous olefin metathesis to give mixtures that can then be separated and processed further into useful, industrially important building blocks. Another important, and so you'll see as we go down this table, I'll just say a few sentences about each of these different types of reactions. I've drawn these as all as being in equilibrium, just to emphasize that in general, olefin metathesis reactions are under thermodynamic control. There might be some exceptions as we go down this list, but I drew it this way just to emphasize that point. And so for the reactions to be driven forward, there needs to be some kind of thermodynamic driving force, generally speaking. So in ring closing metathesis, that thermodynamic driving force is typically evolution of a short chain alkene. This is most commonly ethylene or propylene. And this works, I would say, surprisingly well to close a range of different ring sizes. The ones that are difficult to close are middle ring sizes, so like 7 and 8. but you can, and then very short ring sizes like 3 and 4. But 5-membered rings, 6-membered rings can be closed readily using ring closing metathesis, as well as macrocyclic rings, anything 9 or 10 plus. And this was conceptually first developed by Greg Fu when he was a postdoc with Grubbs. We'll come back to one relevant example of this and one of the problems of the day. Another very important application of Olefin metathesis is in ring opening metathesis polymerization called ROMP. And so here the idea is that you have some strained monomer that can be engaged with an olefin metathesis initiator, and then the result is that you have a propagating a polymer chain, and that as it's growing has a reactive end group, and these types of systems are called living polymerizations. They're important because they allow you to make copolymers. For example, you could first dump in monomer A, that runs to completion, but then your polymer chain still has a reactive group on the end, so you can dope in a second polymer B and access highly defined AB block copolymers. And we'll hear a lot about applications of ROMP in one of our industrial lectureships from the folks at Materia. So Materia is a spin-off company from the Grubbs Group up in Pasadena. Historically, they did both catalyst development and materials development, but they recently sold the catalyst development arm to Umicore. So they'll talk extensively about materials applications of ROMP. Another type of polymerization is ADMET polymerization. This stands for acyclic diene metathesis. And so this is essentially analogous to ROMP, but now it's not driven by ring strain, so you can imagine the inputs here are different. And this reaction, typically to work well, requires removal of ethylene. Have cross metathesis, moving down the list, and we'll talk about selectivity rules for cross metathesis. I think for those of us in the audience who are in the class who are more synthetically oriented, probably the two versions of metathesis you're most likely to run are cross metathesis and ring closing metathesis. So we'll pay special attention to cross selectivity rules. And then two different forms of E9 metathesis. I think when I first learned metathesis and E9 metathesis, I had difficulty predicting products from the starting materials, but I think there's a useful mnemonic, which is that essentially what's going to happen at both of these two alkynyl carbon atoms is that each of them is going to gain an alkylidine from the alkene that's involved. So you take this alkylidine, which is half of this alkene, stick it here, take this alkylidine, stick it here, and then that's how you get your products. So it's sort of a double alkylidine stitching. And so this reaction can be done, of course, in an intermolecular sense or in an intramolecular sense, so in a ring-closing E9 metathesis version. And so again, the way to think about this is you have alkylidine stitching. This alkylidine is going to go here. This alkylidine is going to go here. We'll work through this in one of the problems of the day in just a minute. So now I'll just comment on some of the chemoselectivity trends across what are now commonly used metathesis catalysts and synthesis, as well as some more historically important catalysts like the titanium one I've shown here. And so all of this, if you don't want to write this down, this information almost in verbatim form can be found in this Accounts of Chemical Research by Tina Trinka and Bob Grubbs. But I repeated it here rather than just make a handout to try to make a couple points and to discuss this a little bit further. And so I think that one of the points that one commonly hears in comparing, for example, the molybdenum-based systems and the ruthenium-based systems is that the molybdenum, and I would put tungsten under this umbrella too, these systems tend to be more air and moisture sensitive and typically require glove box chemistry. And while that is true, I think a equally important, if not more important, point is the functional group compatibility trends. And so as you move left on the periodic table, the metal carbines that are metathesis active tend to be more oxophilic and less carbophilic. And so if we think about titanium, for example, we know from thinking about reactions like reaction of the Tebbe reagent with an aldehyde, that these metal carbines with early transition metals tend to react quite quickly with any oxygen-containing functional groups, and indeed that's the case. So they can react with protic functional groups because the carbons here are quite Lewis and Bronsted basic, and they can engage with carbonyl-containing functional groups, as we've covered earlier in class. And so they really only promote effective olefin metathesis if the olefin is the only thing in solution. As we move right on the periodic table, tungsten and molybdenum, these are the Schrock family of catalysts. These have been developed through really elegant work over the course of 2 decades. They're extremely reactive. So in general, tungsten molybdenum-based systems, in terms of catalyst turnover, are much more reactive than the corresponding ruthenium systems. And there are some applications you could imagine in like alkene homodimerization and things like that, where high activity is really important. But they have these are also relatively oxophilic metals, and so you'll see that they are indeed more carbophilic, but they're still quite oxophilic. So some of these more challenging functional groups, alcohols and aldehydes, are challenging to use. I think this has been something that the Schrock group and the Hoveda group have worked really hard on and made some progress on. But in general, these are the trends. And then with ruthenium, the corresponding ruthenium carbines have just this magical affinity for alkenes. And so they'll react with alkenes in preference to almost everything else. And so one way to think about this, and this is discussed in one of the first Grubbs papers on well-defined ruthenium carbene that I'll put the citation up on in just a minute. But remember that all of these, if we think back to earlier in class, we would quite confidently describe as sort of classical Schrock-type carbines, where you have an early transition metal, relatively high oxidation state. And then this ruthenium carbene does not really fit that description. It also doesn't really fit the description of a classical Fischer carbene. And so it lies somewhere in between. And as we talked about, there's this, though we think of Fischer carbene and Schrock carbene as being distinct for the purposes of formalisms, in reality there's a continuum. And the ruthenium, I think part of the success of this family of catalysts is that they lie in the middle of this continuum. And so the ruthenium Grubbs family of catalysts are highly reactive with alkenes, and these reactions can be run in the presence of water, free alcohols, aldehydes, et cetera. And so one way to quantitate or quantify what I just described qualitatively is to just look at the electronegativities of the metals that are involved in metal carbene bonding. This is not the whole story, because remember, ligand effects here can be really profound. But if we just look at this first order approximation, you can see that the elements on the left of the periodic table are, of course, much more electropositive than those towards the right of the transition metal series. And so one might expect, and I think indeed is the case, that the metal carbene goes from being much more polarized in nature in these cases to much more covalent in nature in the case of ruthenium. Okay, any questions on that? So let's talk about then some general mechanistic features, and then we'll jump into the first two problems of the day. So the evolution of mechanistic understanding in Olefin Metathesis is a really interesting story. We'll spend some time in class today on this. The reaction itself is quite old. It's known for more than like 70 years. And reactions like this, where you're seemingly breaking the strongest bond in the molecule, are quite odd to think about. And so I think in contrast to some of the other industrially important reactions we've covered, like hydrogenation, hydroformylation, this reaction really was quite, remained mysterious for the better part of 15 years after its first reports. And in that way, I think it's somewhat analogous to what we learned about at the very beginning of class with Werner complexes, where people knew the structure, they knew what elements had to be there, but the bonding was quite mysterious and really took a lot of dedicated work to elucidate. Okay, so here's the now commonly agreed upon mechanism just in general form. So what I've drawn here is just a homodimerization of a terminal alkene to give the 1,2 disubstituted product and ethylene. And so these reactions generally will begin with some initiation step to get the active catalyst. So in the case of ruthenium, the first step will be dissociation of the phosphine to open a coordination site for the alkene to bind. And then there'll be an initial metathesis step to get the propagating alkylidene. That will undergo alkene coordination, 2+2 cycloaddition to give a metallocyclobutane, which can then fragment via retro 2+2 to give a propagating, in this case now, methylidene. In general, methylidines are not very stable. They can be susceptible to attack from different nucleophiles in solution, and this is a common deactivation mechanism. So, for example, when you dissociate a phosphine here, and this is sitting around in solution, it can come back in, and that can be a deactivation pathway. Nevertheless, it can react by coordinating an alkene, forming a new metallocyclobutane, and then the dance goes on and on. In this case, all of these steps I've drawn as being in equilibrium. Then the irreversible step would be loss of ethylene out of the reaction path. So in practice, a lot of like cross-metathesis reactions, when you run them in practice, or at least when my coworkers and I ran them in practice in the Grubbs group, you'd set everything up like in the glove box, and then you would just leave it running open with the vial open to allow the alkene, and sometimes if you want the solvent to evaporate as well. If you need more controlled solvent amounts, then you have to think about a way to do this. If you want to do it on more larger preparative scale, then you can have a constant stream of argon or nitrogen bubbling through your reaction mixture as you're running it. So these are things to just think about practically as you might want to do this chemistry. Okay, now let's consider problems of the day 1 and 2, which will allow us to apply some of the reactivity principles that we just learned about. So first, let's consider problem of the day number 1. And so why don't you think about both of these, discuss them with your neighbor, and then we'll go from there. I'll just read them out loud so that everybody has the key points. So problem of the day 1 is an example, early example of E9 metathesis from the Katz laboratory. And so based on thinking about mechanistically how this chemistry might work and applying the mnemonic that I just mentioned, predict the 2 products under the different reaction conditions. And then question 2 is an early example of ring closing metathesis from the Grubbs group, but using a Schrock catalyst or complex. And so predict this product. So first, assign electron count, oxidation state, etc. of the Schrock catalyst, and then predict the product and explain mechanistically what's going on. Okay, so let's take a minute to think about that, and then we'll reconvene. right, let's reconvene and get some thoughts on the board here. Max Moore, what do you think?
For number one, the catalytic amount, I would just do the Engle metathesis. I'm not sure what you would call it, but the 6-membered ring, and then like a alkene hanging off, and then a methyl off the top.
Okay, so a 6-membered ring, and then off of one of these you have a methyl, you said, the alkylidine with a methyl, and the other is what?
And the other, I don't have a good answer. I made it silly, but I don't like it.
Okay. So this is what you had for the first one? Or am I getting it wrong?
I might have added a carbon.
We're not sure about. Okay. Anybody else get something the same or different for B and want to provide their thoughts on A?
That one is A.
You think this one is A? And then what would B be? Ein metathesis. Okay. That's an interesting idea.
Or maybe for A, you can have, so basically after the tungsten alkylene engages with the alkyne, you have another equivalent of that intermediate coming in, and basically we swap the tungsten to the terminal position.
Okay. So you're thinking this one would have the, what is the carbene from the Fischer carbene? Is that what you had in mind?
Yeah.
If I don't have this right, then just let me know what you're. Okay. So you wanted to react the terminal one with this. Is that right? Is that what you had, Brendan? Oh, no, you actually had this as the tungsten alkylidine.
Actually, so could you just draw the intermediates where tungsten alkylidine engages the
Okay, yep, that's a good idea. Let's just walk through mechanistically what's happening here. Okay, so in the first step, the group, so remember the first step is reacting your metal, whatever metal carbene you have. And so let's consider the stoichiometric case first, because this one there's actually no catalytic cycle, so it's the easiest in some ways to think about. So the first step is going to be the carbene engages with the, let me just really draw this out in detail so everyone can see. With the alkyne. So first the alkyne coordinates. Then you have a 2+2 step. And then a retro 2+2. Actually, I'll just draw it to the right here so I don't know what's squatting down. And now we just have simple ring closing metathesis.
Maybe one more carbon.
These are not the problems. This is seven. Is it just like a yeah.
Is this step happens with the opposite selectivity? Okay, so the first step is the opposite. Thanks. Okay, so the first step, coordination of the alkyne. So in general, in systems that have an alkyne and alkene, you'll react preferentially with the alkyne first. Bless you, 2+2, retro 2+2. So this transfers this carbene to the terminal position, and then you form a new metal, tungsten carbene, and then that can undergo cross metathesis to form what is this new bond here. and then generate as the product, which I had, right, the tungsten methylidine. And so then the question, so with a stoichiometric amount of metal, this takes place, and this sequence is faster than the rate of further propagation with this methylidine. In the case of catalytic tungsten, now this comes in and engages in this initial step. And so the product that one gets out here is the major product that one gets out here. So you will get some, let's say 10% of this product, but in this case the major product will be this one. This is this. Okay.
So which one is which?
What do you mean, which one is which?
Which one are you saying is A and which one are you saying is B?
A is the top one. B is the bottom one.
You still get out 10% of A catalytic, or
Yes.
does it come back into cross metathesis?
You will get 10%, give or take, of A in the catalytic conditions. Any questions, additional questions on that?
So, stoichiometric, why does it not react again with the tungsten?
Yeah, it's just, in this case, this is a relative rates question. So the rate of the initial Fischer carbene engaging the alkyne, in this case, is faster than the rate of propagation. Elena.
What does it stop? How does it your new tungsten carbene interact with the alkene?
Yeah, I think, yeah, that's the question Nick was just asking. So it's a question of the relative rates of the initial sequence versus the propagation. And in this case, the initial reaction from the Fischer carbene is faster. And so that's happening, let's say, 10 times faster than the propagation part. And so all of that happens, and then it's done, and there's nothing left to react with.
Stoichiometric, are you saying in all of the one mixture at the end?
No, yeah, so I think it's because when you form the methylidine, that engages with the alkyne, and that's what gives product B, instead of engaging with product A. Yeah?
I couldn't hear what you just said. But.
Yeah, so I said the metathesis between product A and that alkylidine could not, it is out-competed by other processes, right? So the question was whether product B can be formed from A by metathesis with this alkylidine.
Right, yeah, and the answer to that is that this is not a very reactive metathesis partner, this alkene, because it's too highly substituted, and it's a still beam.
So they coexist at
Yes.
the end.
Okay, problem of the day number 2. Xiaochun, what do you think?
Oxidation is +6, and the electron is B0, and the overall electron is 12.
Okay. +6, D0, 12 electron. Anybody get anything different? So let's quickly walk through this. How many X-type groups? You have 2 alkoxys. you have a linear amido, which is what? Okay, it's LX2, and then a Schrock carbene, which is X2. So that puts us to +6 oxidation state, molybdenum, in this case D0, and then what's the electron count? Two electrons from each of the alkoxy, that's 4. 4 from the Fischer carbene, that's 8. 6 from the linear amido, which is LX2. Gets us to 14. Everybody got that? Okay, and the reaction, Xiaoqun. Okay. So you want 2 + 2 first between the alkene and the metal. So I'm just going to draw this as here, and this will be, okay, what from here? Okay. To generate a new and this, I think, connects to the question that Elena was asking, and the product that we get is this this sterically encumbered alkene that is going to be relatively inert to metathesis. And then what? And then the 2 + 2 with the ketone, okay? Okay, and then walk us. We're almost there. Get us home. Okay. One more metathesis. To give molybdenum oxo. And corresponding cyclic alkene product. This is an early example of carbonyl olefin metathesis. Happening concomitant to some of the early reports in ring closing metathesis. Anybody got anything different or questions on that? Yeah, B.
The oxidized can still re-enter the catalytic cycle, or just?
In this case, it's a great question. In this case, the molybdenum oxo is inactive.
Oh.
So that's why the reaction requires one equivalent of the metal. And so in general, in this type of approach to carbonyl olefin metathesis has not really been rendered catalytic because of the difficulties of converting the metal oxo back to a propagating carbene.
the coordination environment change the stability to like the oxygen as the affinity to the carbon? Because in molybdenum, you were saying that it's more affiliated with oxygen.
So if we look at molybdenum, then we see that alkenes are still terminal alkenes are still preferentially reactive to ketones. And so the success of this approach is predicated on having the ketone be the carbonyl coupling partner. So it can engage first with the alkene and then intramolecularly with the ketone. Does that make sense? So it's hopefully a useful example of these selectivity rules in practice. Yeah?
In the previous problem, how does product catalytic form B is formed? The catalytic one, not the dimension.
How is B formed? Okay, yeah, so in this case, after the first 10% of the tungsten carbene initiates, then now, as the reaction is propagating, you have so it initiates just like here. But now, as it propagates, and so you end up transferring so I've probably drawn these in a confusing way, which is probably creating some problem. It's maybe easier to think about. Does that make sense? So then this rotates around and bites back in. This one is this. Okay, one more question, and then if there's additional questions, we can talk.
I guess I'll ask also why is it a Z isomer as opposed to E?
Why is it?
And ends up methyl Z to the
Yeah, it's a good question.
because generally it's E selective, right? In metathesis, usually you get them.
Yeah, normally the reactions are under thermodynamic control,
Yeah.
and thus the reaction outcome is a thermodynamic ratio of about 2 to 1 E to Z. And then in this case, the reaction is under kinetic control. And maybe after class we can take a look at the metallocyclo butane that's involved and why it's this way. It's not a critical point except to say that there's no secondary metathesis that causes isomerization in this case. Does anybody need any of these notes? Raise your hand. If you do. Okay, let's take a look at some of the early history that sparked interest in this transformation. And a lot of the first reports were coming out of industry. And so one of the first relevant discoveries was out of DuPont. And so we talked briefly about Carl Ziegler and his contributions to polymer chemistry, the advent of the Ziegler-Natta polymerization. And so one of the interesting discoveries that took place at that time was that when norbornene was subjected to Ziegler-type conditions, and the expected outcome was just polymerization across this alkene in the same way that a typical polyethylene or polypropylene polymerization would work, then they were somewhat surprised to find that the product was actually polynorbornene containing, and the key indicator was that it contained an alkene. So mechanistically, there was something going on here. And then there was a report from Phillips Petroleum that attracted significant attention. They found that they could take propylene under these heterogeneous conditions, very forcing, high temperature, high pressure, and get out a distribution going in with C3 feedstock, getting C4 and C2 products. So they called this reaction olefin disproportionation. And then another of the, so there's an interesting interplay, I think, of polymer folks and petroleum folks who kind of sparked the initial seeds of this. So now you're already starting to see appearance of some of the more active metals. So this is work from Natta, who found that cyclopentene could be polymerized. And then in the late 1960s, a couple key reports from Calderon, who was one of the first to make this connection that the results in the polymer world, these two, and in the alkene disproportionation world were perhaps mechanistically related. He found that under heterogeneous conditions, you could get polymerization of cyclooctadiene and get this alkene disproportionation. And the ratio here between C4, C5, and C6 is 1 to 2 to 1, which has important mechanistic implications. So as I mentioned, the question on many people's minds was, how are these somewhat bizarre reactions happening? Because they certainly don't look like what was commonly known at that point. And so one of the things that was known I'm going to draw this just with deuterium labels so everyone can so we can be precise on where every atom is going. But one thing that was known was that the partners on a single carbon atom stayed together. And what was not observed were any of the possible cross So people put forward a number of what now look to be quite creative pathways. So Calderon, who I mentioned earlier, put forward a pathway that looked like this. Where he was thinking about the potential involvement of some ambiguously bound cyclobutane intermediate. But it was known that cyclobutanes were not observed. Formation of cyclobutanes was not observed in any of these recently reported olefin metathesis reactions. And it was also known that if you put a cyclobutane in and hoped to engage it in this chemistry, it also did not work. And so Luandos and Pettit at UT Austin proposed something related, which is that to avoid the potential involvement of something that's going to look like a cyclobutane, you could have scission of all of the alkenes to the corresponding carbenes, and then some inventive-looking complexes could be generated. So for carbenes like this that could also be formulated like this. And these pathways, and the one I'm going to draw in just a minute, were called pairwise pathways, because they require that in some way, shape, or form, both alkenes are on the metal at the same time. And the Grubbs group was involved very early on, essentially immediately after Grubbs moved to started his independent career at Michigan State after finishing his postdoc with Coleman at Stanford. And so he put forward a pathway that involved metallocyclopentanes, which start to look more like things that we encountered, that we are familiar with so far in the class. But one of the things that was a little uncomfortable about this pathway is that there needed to be some somewhat unusual looking shift. And he proposed that this took place via actually a cyclobutane carbene, which I'm happy to draw out after class if anybody is really interested. But this was also not quite right. And then the first proposal of the what we now know to be the is now agreed upon to be the correct mechanism, the so-called Chauvin mechanism, was by Chauvin, working in France. And so the key insight was that was a proposal of a metallocarbene intermediate. And so one of the things that you might ask yourself you might be asking through the lens of everything that's known now is, why didn't anybody propose carbenes earlier? And at least one of the reasons is, if you think about the timing, remember this is all late 1960s, early 1970s, and Fisher's first report of Fisher-type carbene was in mid-1960s. Schrock's first report of Schrock-type carbene was early 1970s. And so even though these were beginning to become appreciated in mainstream organometallic chemistry, they still were not so widely encountered that that they would immediately come to mind. And so in an interview, Chauvin said that how this came to his mind was actually thinking about these results from Phillips Petroleum, and then thinking about Fisher's report of the Fisher carbene, and sort of making this connection. And so there's some debate in the literature of so I think the fact that Chauvin was the first to make this proposal is not really debated, but I think there's some debate over who was the key player, or who were the key players in confidently elucidating that this was indeed the mechanism. I'll just highlight two very important papers from Casey and Katz. in the mid-1970s. And so one of the things that's interesting to note is that after Chauvin's initial paper, there are basically no citations of this for almost the better part of 2 or 3 years. And so, and that's in large part, I think, because of the journal that it was published in, the polymer journal. And so I think it's very likely that other people were developing the idea of a carbene-type mechanism independently. And then in this flurry of work in the mid-1970s that coincided with Schrock's discovery of the Schrock-type carbene, that people really put the nail, hit the nail on the head here. And so the key insight from this that then really propelled this whole area of research was that the metal carbene is the active catalyst. And for anybody who is interested in this early history, I would recommend this. There's a great CNE News article pre-Nobel Prize that really paints a comprehensive picture of this. So the problem, so the key insight was that a metal carbene is the active catalyst. The problem was that all known metal carbenes at that point, the early Fischer carbenes, as well as the first Schrock-type carbenes, were not metathesis active. So this is sort of the mid-1970s at this point. And so I think everybody probably has recognize the chemist of the day when you came in, so I'll just I'll spill the beans. I tried to find a young enough photo that it might be non-obvious, but I don't think I succeeded. So this is, of course, Richard Schrock. We've heard the name mentioned several times for several key contributions, so I think it's fitting. His education was somewhat local. Started at UC Riverside, PhD at Harvard, as we said, as we learned with Osborne, postdoc at Cambridge with Lewis, who is a contributor to cobalt carbonyl cluster chemistry, and then early affiliation with DuPont, and of course quickly moved to MIT. Walk us through the chronology of the Schrock family of catalysts, Grubbs family of catalysts, and then we'll, sorry about that. I'll walk us through the chronology of the Schrock family of catalysts, the Grubbs family of catalysts, and then we'll conclude by quickly looking at the 2 remaining problems today. So we've seen this tantalum alkylidine complex now several times. As a reminder, this was 1974. This was metathesis inactive, but of course, after the work of Chauvin, Katz, Casey, Grubbs, these folks, there was active interest in finding a well-defined metal carbene that was metathesis active. And that came in 1980. And then the race was on to develop this structure further. And it was found quite early that by moving to the right of the periodic table, some of the issues we mentioned before were improved. Which, over the course of about 10 years, led to the overall core structure of the catalyst that we now sort of recognize today. So these catalysts certainly take the cake for reactivity. And you see in some of Grubbs's work in trying to develop this chemistry in synthesis, he indeed used the Schrock catalysts. And so the Grubbs family of catalysts started gaining steam in the early 90s. And so this line of inquiry is kind of an interesting story. It came from a reaction that they were trying to do in the context of a polymer project, trying to polymerize an oxanorbornene to use for applications in ionophore gel compounds. And it was known in the literature that if you added ruthenium trichloride hydrate, that this, under aqueous conditions, this turned into something metathesis active. And so they themselves used the mixture and found that it indeed works, and hence the implication was that there should be a ruthenium carbene involved. And Son-Bin Nguyen, some of you might recognize his name, is now a professor at Northwestern, was the first to prepare this metathesis active ruthenium carbene. That led to this we would call G1 a few years later. And then the Hoveda laboratory made an important contribution by developing this chelating benzylidine, which imparts improved stability, and in the case of these NHC-containing catalysts, also renders the overall catalyst phosphine-free, which, as we just mentioned, is important for suppressing certain decomposition pathways. After Arduengo's report of the first stable NHC complex, people like Wolfgang Hermann, Steve Nolan, Grubbs, others started exploring the reactivity of complexes containing NHCs. So there were several reports, as well as Furstner, I should note as well. Furstner, Hermann, and Nolan all reported this generation, where the key is that this is a IMES, and the reactivity was not so good. And then Grubbs, shortly thereafter, reported the SIMES containing version, which is now what we know as Grubbs 2. One of the key points I want to make is that after a single metathesis turnover, the identity of whatever this group is inconsequential. So whether this is the vinyl carbene, benzylidine, Hoveda benzylidine, that the propagating species in all the cases is the same. And if you eventually work in polymer chemistry, you'll very likely work with this catalyst, which contains 2 pyridines. And in the polymer community, people call this Grubbs 3rd generation, G3. So let me just articulate some of the key discoveries that summarize a lot of work. So introducing this SIMES ligand makes the catalyst much, much more reactive, albeit slightly slower to initiate. And the key here is that after dissociation of the phosphine, then the catalyst has a choice. Does it reassociate the phosphine, or does it find an olefin? And with a SIMES here, it becomes about 10,000 times more likely to bind an olefin, and hence the catalyst becomes much more reactive. As I mentioned, when you have this combination of SIMES and phosphine, the initiation is quite slow, and that's problematic for materials applications where you typically want fast. You want initiation to be faster than propagation. And so by replacing this with these pyridine groups, which immediately dissociate in solution, you can get very good polydispersities in polymerization chemistry. Okay, we're a little bit over, but let's just quickly go through problems of the day number 3 and 4. In the interest of time, why don't you look at them and I'll start writing them up. So problem of the day number 3. Anybody have any ideas? As I'm just first going to draw the structure.
This is just hydrometallate and then aluminum chloride to make a vinyl carbene.
Very good, Saul. So this is a ruthenium hydride dihydrogen sigma complex. I've actually worked with this myself. It's surprisingly stable. And so Saul's proposal was, okay, let's say the first step, it's going to lose H2 to open up a coordination site. The first step will be hydrometallation. And then the next step will be d electrons from ruthenium come back in to make ruthenium carbene, vinyl carbene, as Saul said, and lose chloride minus. And so you might make a connection that this motif looks like this motif. In the first version of this, it was actually made from a cyclopropene, but this is one of the routes that's used industrially to generate the carbene. So one of the questions you might ask is, where does the carbene come from? Normally it comes from either this, at least for ruthenium, either this or from a diazo compound. Okay, and problem of the day number 4. Just in the interest of time, I won't draw out the whole product. But are there any thoughts on, so this is really a chemoselectivity question. So this molecule has several different potentially reactive groups. I'll give you a hint and say the TIPS group on an alkyne basically masks the alkyne. So that is not going to be relevant. So now you have 4 alkenes. Which would be the first to engage? And shout it out if you have an idea.
The terminal one with no substituents next to it.
The terminal one with no substituents, which is, I think, the leftmost. Is that right, Hannah? Okay. Very good. So do you think that's a steric argument?
Yeah.
Okay. That's certainly true. And there's another hidden part of this, which is that chalcogen groups at the allylic position are known to have a special effect, essentially a directing effect, in accelerating carbene formation proximal. So this is called the allylic chalcogen effect. It works with alcohols as well as sulfides, most commonly. And I want draw out the stereochemistry. So what will happen now is that this ruthenium also has a choice. It can react with 3 different alkenes, but only one of them can close to form a 5-membered ring, and that's this one. Okay, and from here, any thoughts on the last ring closure? Right or left? Right. Why is that, Hannah?
The test group shuts down that effect.
Yeah, and I think the ring size is different. 1, 2, 3. This would close a 4-membered ring, and this would close a 5-membered ring. And so this strategy, so you could imagine, were this group not here, say you just had this vinyl, then this would be a real mess if you put it in with ruthenium. Well, maybe it's not going to be a mess, but it's going to be very hard to control with high fidelity which of these alkenes the catalyst first engages with. So this is a strategy developed by Tom Hoy's group called relay ring closing metathesis, where you can install essentially a sacrificial directing group to put the ruthenium carbene exactly where you want it to drive a single metathesis event. Okay, very good. Sorry, went a bit over today. Happy to answer questions. Thank you.